Привет.
Алло, привет.
Так, сейчас будем делиться.
Сейчас мы будем сначала убирать virtual background.
Все, поделился. О, черт, подожди. Я записываю всех, оказывается.
Integral realization of S.Shadrin, because so my favorite one is different from the previous week, from the one that Pierre Guy has introduced, so the one of Shpaton, Fomin, and Zerevinsky. So my favorite realization is Laday's realization. So to construct the Laday realization of S.Shadrin, so what we have to do, so look, I mean, we have to list all binary trees with fixed number of leaves. So in this case, it's n leaves for me, right? And so, okay, so in this case, it's 4, to be more precise. And then at each vertex, I mean, so if I have n leaves, then I have in my graph, in my binary tree, n-1 vertices. I have to compute the number of left descendants, right descendants, I mean the number of leaves that I would meet if I would go to the left or to the right from this particular vertex, and multiply these numbers, right? So for instance, I mean, for this point, I have 1 leaf on the left and 1 leaf on the right. So I have here 1 times 1 is 1. For this point, I have 2 leaves on the left and 2 leaves on the right. So it's 2 times 2 is 4. And for this guy, I have 1 leaf on the left and 1 leaf on the right. So it's 1. Right, so it's number of left descendants times number of the right descendants for each vertex of my graph. So then I get some integral coordinates in some, well, vector space, and this is the realization of S.Shadrin that I want to have, right? So here are some examples. So if I have n equals to 2, so I just have just one binary tree, is this one. So then there is nothing to compute, it's just coordinate 1 in one-dimensional space, right? So it's just this point is my S.Shadrin. If I have n equals to 3, then I have 2 possible binary trees. And so this one gives me 1, 2. This one gives me 2, 1. And then I have a closed interval, right? In the case n equals 4, so I had to list all the binary trees. There are 5 of them that I have in this case. So, and I computed for you. So for instance, this 1, 4, 1, we have already seen, but for instance, so let's check this one, right? So it's, for this guy, I have 1 descendant on the left and 2 descendants on the right. So it's 1 times 2 is 2. So then I have the next guy here, if I go from left to right, is this guy. So then I have here 1 descendant on the left and 1 descendant on the right. So it gives me 1. And then the next guy is this one. I mean, I always list them from left to the right. So for this guy, I have 3 descendants on the left and 1 descendant on the right. So it's 3, right? And then I didn't know how to draw a picture. So, the only idea I had, I mean, so when I computed all this, to draw the projection along x1 on the plane x2, x3. But the point is that, so what I want to stress is, what we see now is that all these points, they lie in a particular hyperplane, in Z3 or R3, so probably I should say Z3 because I'm interested in integral polytopes, right? And this is a general phenomenon. So when I do like that, I always get a S.Shadrin, but this S.Shadrin is of 1 dimension less than the dimension of the space, and it's always in the hyperplane. The sum of coordinates equals to so n-1 factorial, right? So that's, I don't write it here, but I just want to say that, yeah, so what I want to say about these guys, you see, I'm not going to study them in detail in this talk, right? So the only thing I want to say is that, so once we have this S.Shadrin, so integral polytopes actually, so then we can go further and construct the toric varieties for these integral polytopes, right? And now look, I mean, so so what I want to say is that, okay, so for, well, purely for dimensional reasons, I know that I get this C star to the power n-1 action on these toric varieties, but because they all are in, okay, so as I already said, in this hyperplane given by the sum of coordinates is equals to n-1 factorial, I know that when I look at this natural torus action on the varieties that I construct, I should have diagonal action trivial, right? And so then I can say a few more things, and so I don't want to go into details, and you will understand why in a few minutes. But okay, so fixed points of my torus action are just the vertices of Ladé polytopes of Ladé S-Shadrin. So they're just indexed by play binary trees, right? So then if I am thinking about one-dimensional orbits of my torus action, so then they are in correspondence with the plane trees with one ternary vertex. So I mean, I have to look at the edges of one-dimensional faces, better to say, of my S-Shadrin, and I can continue further. And the point is that so I know that the faces of S-Shadrin are in correspondence with the plane trees on the one hand, right? On the other hand, so I know that they should be in this construction in the correspondence with the torus invariant strata in my toric variety that I get, right? So I get actually not just a variety, but I get a natural stratification of this variety where all strata are torus invariant, and so they correspond to faces of S-Shadrin. And if I would think a little bit more about what is so nice about this presentation of Ladé of S-Shadrin is that each stratum is in some sense in correspondence with the product of the standard Ladé S-Shadrin. I mean, the same representations of the same integral representations. So it means that somehow, I mean, the certification that I have, it has this recursive nature. Namely, if I look at the particular torus invariant stratum corresponding to particular plane tree, then it would be just a product of these toric varieties of small dimension, right? And now, I mean, I promise that this talk is going to be completely independent from the previous one, and I'm going to keep my word. But if you have seen some natural varieties with this property in my previous talk, then this is exactly the same. So there is a theorem. There is a theorem. So maybe I have to write here some theorem. So theorem by Laura Escobar. So which says that these toric varieties are actually the same as particular Bode-Samuelson varieties known as brick manifolds. So, but I'm not going to use it today. It's just for your information. So my goal today is actually you see. So I already said everything I wanted to say geometrically about these guys, right? And I'm not going to go into the details how they work, but I want to now discuss all the algebraic structures in the title, and from these algebraic structures make, well, partly a conjecture, partly a theorem. Make conjecture, but well, so there is some conjectural statement, but also there's a theorem. Well, about how these varieties, or more precisely, how the homotopy equivalent versions of these varieties, but homotopy equivalent in the sense that they would be compatible with all these certifications that I mentioned, occur topologically, right? And yeah, so to talk about that, I need to develop some particular language to talk about algebraic structures. And this is the language of operats. And I'm going to sort of not really make a crash course on operats, but just to tell you how I'm thinking about algebraic structures. And you will see that it's a kind of natural way if I want to talk about algebraic structures, but do not recall any examples of them, which is basically what I'm going to do today. So the point is the following. So when we have some algebraic structure, for instance, associative algebra, commutative associative algebra, Lie algebra, Poisson algebra, or whatever else, the way we can think about them is to say that we have some operations that have inputs, so labeled 1, 2, 3. So for instance, 3 inputs and output. So these guys are my inputs and this is an output. And so then instead of thinking about particular realization of this algebraic structure, there is a chat message I see. Okay, success. Good. So so we have inputs and outputs, and the point is the following. So if I don't want to think about examples, so I would just say that we consider the space of operations abstractly. We just list all the possible operations that we can have for this particular algebraic structure and consider, instead of particular realizations of these operations in a given, I don't know, vector space, we just consider these operations at the spaces themselves, right? So to this end, I would have, okay, so this is my notation. So this is a concept of opera that does it. And so I would speak about, so ON is just a space of operations, all possible operations that I want to have of arity N. Arity N means n inputs, one output. And of course, I have there a natural as an action, typically, because I can reshuffle the inputs before applying the operation, right? And another piece of the structure is, of course, when I have several operations, I can just first apply one operation, get the result, and then plug it into the other operation as one of the inputs. And so these are so-called partial operatic compositions. So I denote it by circ-E. Circ-I means for me that I just take the result of this operation that I got here and plug it into the operation that I have here in this space as the ith input. So ith input, it's written here, right? And so then I get an operation with this many inputs. So let me draw you a picture. So this is my first operation with n2 inputs. So then I say, aha, I have another operation where I want to plug it in, right? And so this I just tells me that I plug it as the, for instance, in this case, second input of this other operation that has in principle n1 input. So one of these inputs is now consumed to plug the output of this guy. That's why the total number of inputs of this new operation is n1 plus n2 minus 1, right? So this is a way to think about algebraic structures abstractly without going into examples. And still, it's good to understand how it's related to the usual structures that we used to think about. For instance, what happens if I just have an associative algebra? If I just have an associative algebra, that I can take any n elements of this algebra, any permutation sigma, reshuffle these elements with using this permutation, and then multiply all of them from left to right using my associative product, right? So then I can denote this operation, this particular operation by, I don't know, this graph, and say that I consider a linear span of all graphs like that. So this would be my Sn, so the space of operations of arity n in the operatic that controls associative algebras. And of course, I mean, so after I told you that we have these operatic compositions, we see that we can develop the usual sort of algebra for operators as well. Namely, we can generate, for instance, freely by some given set of operations, all possible operations. We can define what is an operatic ideal. We can define what is a morphism of operators and so on. So all of this routine algebraic stuff can be routinely generalized for operators. So for instance, if I would try to define an associative operator, then I would just say that I consider a free object in this realm of operators generated by two operations when I multiply two guys and one, when I reshuffle two guys and multiply them, right? And then I can generate any multiplications like that, just put in brackets here. And then I have this ideal that generated by these guys actually saying that my product is associative, that the possible brackets that I would put can be ignored, right? So the same I can say, for instance, more examples, like what is commutative algebra? Commutative algebra is roughly speaking the same, commutative associative, of course, algebra, commutative associative algebra. So I just take some operation, which is from the very beginning, it's a binary operation, but it's totally symmetric. It's already commutative. From this, I generate all the possible operations I can. And the only condition that I have is that this operation must be associative, right? So then I'm, okay, so my favorite way to think about Lie algebras is not to have Lie algebras, but to have shifted Lie algebras. Shifted Lie algebras, that's, yeah, might be related by the fact that I'm living in the Netherlands, because, yeah, so the typical example that I would keep in mind is this Schouten bracket. So namely, I would say that we still have a symmetric operation, so which is my shifted Lie bracket. And then, okay, so I have written here associativity, but that was totally wrong. I meant, of course, the Jacobi identity. So Jacobi identity for this shifted Lie bracket. So, and the point is why I really want to think about a shifted Lie bracket, not the usual Lie bracket, because the most natural example of Lie bracket, so the Schouten bracket on polyvector fields, is exactly an example of the shifted Lie bracket with respect to the natural grading on polyvector fields, right? So, I mean that I want these guys to have a grading, I have to think, minus d1, right? So this has degree minus d1 for me. Good. Okay, so that's how we think about this kind of guys. And yeah, I have more examples because you see, I listed a lot of examples in the title, and I feel that I need to introduce all of them properly. And to be honest, I will need all of them. So let me also say what is a Gerstenhaber algebra. So Gerstenhaber algebra is also a natural structure that we have on the space of polyvector fields. Let me go one slide back. So I have here these polyvector fields, but of course, when I have this kind of guys, I don't always have to take this Houghton bracket, right? I can also just multiply them. So I also have here a structure of commutative algebra, right? And so then the point is that this structure of commutative algebra and this Houghton bracket are compatible in some particular way. And so this is what I want to say here. So that in the case of Gerstenhaber algebra, I have a symmetric commutative product. And I also have a symmetric degree 1 Lie bracket. And the point is that when I try to apply the Lie bracket after I apply commutative product, I have this kind of identity. So maybe it's if I apply, for instance, so 1A to B times C in the usual case, when we think about the Houghton bracket and the product of polyvector fields, is going to be up to some signs A, B times C plus minus, so B times AC, right? That's basically what I want to say. That's the property that we know considering polyvector fields, right? And I made a mistake. So this space here was reserved for some important comment. Okay, sorry. So I will make this comment somewhere else. So the point is the following. So there is another structure, and this is the structure which I like very much, and I'll give an example for the structure in a second, is the so-called BV algebra. So BV is for Batarin-Vilkovisky. So namely, we also have a symmetric commutative product. So two inputs, one output, symmetric commutative product. But then I also have a particular operation of arity1. Arity1, so it means that one input, one output. I denote by delta, and in the pictures I just denoted by this barred symbol, right? And the relations that I would have are the following. So one relation is that delta squared is equal to 0, right? So that's what is written here. And the other relation, look, I have symmetric commutative product, so the usual product, and I want delta to be the operator of the second order. So this relation just means that delta is of second order. So it's the so-called 7-term relation, but it's just to say that some operator is of second order with respect to the commutative associative product, right? So, and the point is that, so BV algebras and Gerstenhaber algebras, they're closely related to each other. And so that's maybe, yeah, so I wanted to say it here, but now let me, so the point is the following. Whenever I have a BV algebra, I can consider the following new operation. I can consider the following new operation that I would denote like that. I would denote it on the one hand like this, and I just want to say that this is a sort of commutator of my commutative associative product with delta. So I would do like that. So you see, and so what I want to say is that whenever I start with a BV algebra, I can construct this operation. It's going to be a shifted Lie bracket, and this shifted Lie bracket together with my original symmetric commutative product would form a Gerstenhaber algebra, right? So it's a quite natural procedure. So once I start with a BV algebra, I can always construct a Gerstenhaber algebra, right? So for Gerstenhaber algebra, we have already seen an example. Namely, an example was the how it's called, the full structure that we have on polyvector fields. So now I want to show you an example of a BV algebra. So example, I have to take holomorphic polyvector fields on Calabi-Yau manifolds. So the point is the following. So what I do, I want to take holomorphic polyvector fields. So this is what I have here with the coefficients in anti-holomorphic differential forms. So these guys are the following. See, operators, the usual is in bar, right? And they, if I would take just differential forms on the Calabi-Yau on any, well, I would say Keller manifold or a complex manifold, right? So they would be with first order with respect to this product, right? But the point is that you see, I intentionally, so this is of course isomorphic on Calabi-Yau manifold. I can use the Calabi-Yau form to say that this is isomorphic. This is isomorphic as a vector space to the space of as vector space. But the point is that this isomorphism of vector spaces is not isomorphism of commutative associative algebras. So the algebra structure that I have on the left-hand side is quite different from what I have on the right-hand side. And so this operator D is of the first order with respect to this structure, right? But it's of the second order with respect to this structure. So that's an easy check, so I won't do it now, but it's just to show you that we indeed have a source of natural examples. And now I want to comment a bit further. So because you see, I mean, I was discussing structures, and probably since I mentioned that some operations should be of order 1 and this kind of things, you probably already realized that I want to work with at least graded vector spaces. But in fact, I have naturally so differential graded vector spaces throughout all this construction that I have. And in particular, we see that what I get here, so what is written in red is extra structure. Namely, it's just a differential that would be of the first order with respect to the product here. It would commute with D. So I mean the differential D bar. So in fact, what I get here is a differential graded BV algebra. So this is a sort of natural source of examples. I will explain later on why this example is particularly important. But right now, I want to say something general about BV algebras. So you see, I mean, when you just have BV algebras, you can ask yourself how to use them. And the point is that, the way I like to use differential graded BV algebras, let us say, is, so I always, well, actually, so we'll see that my only example that I have today is in this realm. So I always try to at least partly homotopically resolve them. So namely, I want to homotopically resolve delta. And I'm explaining here in a very, very naive way what I mean. You see, I have this operation delta, but I don't like that I have this operation sort of independent, right? And I'm saying, aha, but let's say that, okay, so I have my differential. So I now denote it by D, it's my differential, right? But the point is the following. So what was D bar in the previous example? But let me introduce a new operation, new artificial operation that I will call phi1, such that if I would commute with new artificial operation, I would get exactly my operator. In some sense, if I would later on do this, but if I do this, then I get a new cocycle. So if I look at this expression here, so this expression might give me something non-trivial on the cohomology, because if I would now commute this expression, so it's just a linear combination of operations by DG algebra, right? So I get something non-trivial. So I want to introduce an extra operator of this extra cycle that I occasionally add, right? So then I can present another cycle that I possibly added. So I want to kill it as well, and so on. So what I'm doing now, I really don't want to have any non-trivial operations if I pass to cohomology of RT1. So I kill all of them consequently, right? So a way to assemble that is to say that, so I can write this kind of conjugation is that if I would look in what happens in the BV algebra, then this differential D would be conjugated by so exponent of these RT1 operations. So what is written here is altogether still an RT1 operation to D plus Z delta. Z is just a formal parameter. So this is just a formal parameter. And now you see what I want to do now. I want just to go back, and the point is the following. So if I just want to show you that my only example that I will have today, so this polyvector fields on Calabi-Yau manifolds, is exactly the example where I have naturally a natural homotopy solution for my delta. So let me go back. So what I have here, so let's discuss. So here you see, so when I'm thinking, okay, so now you see to discuss, I mean, what is my way to resolve delta, because it's just about RT1 operations. I can take this vector space, and this vector space, I know that I can split it. I know that I can split it as harmonic forms plus some orthogonal complement, And on this complement, I can choose some operator that I would call H. And so on harmonic forms, my H would work as 0, such that so H commutative with d bar is equal to 0, and what else? And H is equal to what? Is somehow equal to my D inverse, right? So maybe it's better to say like that. That H D plus DH is projection to this orthogonal complement to harmonic forms. Projection along harmonic forms, right? So this would exactly mean that my so now maybe I'll change color to write it better. That if I would take now d bar plus zd, so then it would be exponent of minus zh. So d bar, so exponent of zh, right? So here I can stop at the first. So here I do have this. I can say infinite sequence of operators, extra operators that I need to add to resolve my BV operator, which is just around D, holomorphic D. But then this infinite sequence is actually a finite one because all high operations are equal to 0 in this case, right? So very good, very good. So that's, you see, I mean, this naive idea that I want to homotopically resolve all the RT1 operations, it does work in the only example I have. And then to this end, we have this theorem with, I mean, there are a few more versions of the theorem, but I like the one that we have found with Anton Khoroshkin and Nikita Markaryan. So namely, you see, so after I have homotopically resolved all these RT1 operations, I want maybe to give another description of the structure that I get on the cohomology, right? And the structure that I get on the cohomology can be described like that. Of RT3, and I can give explicit formulas, but they're quite complicated explicit formulas of RT4 and so on, the inputs, so totally symmetric. And there would be relations. For the relations, there's no WDV relations. WDV relations. So this is, but I have also seen name as flat F-manifold. So maybe F should be big one, F-manifold. And so it's basically the structure that you get if you think about homological field theory in genus 0 or Grom-Fitton theory in genus 0. So I don't want to write what are these double DV relations. So this is a kind of
condition. Sorry, Sergey,
yes.
Can you repeat condition for this commutative algebra? What you said.
What, to repeat what? Sorry.
Can you repeat the conditions that it is for this flat for what you saw?
Yeah, conditions are very easy. I have differential graded BV algebra.
Yes.
And I just homotopically resolved delta, nothing else. Homotopically resolved delta means I have thrown in all these extra operations, right? I don't have anything else. I just throw in all these extra operations to kill delta homotopically and all its higher homotopies. And then I look at what I get on the cohomology. And the answer is, so what I get on the cohomology is the structure that is, let's say, if you study Grom-Fitton theory or this type of stuff, I don't know, singularity theory, homological field theories, whatsoever, Frobenius manifolds, then it's the structure that you have seen many times. And for instance, I want to say is that, so let me get back to my example. So I go 2 slides back, right? So I can apply it here, right? Of course I can apply. So I'm applying it here, and what I get on the cohomology of my Calabi-Yau manifold. I get some structure that I expected to have, for instance, if I would say, well, this is a phenomenon of so-called mirror symmetry, right? So if I would consider a mirror pair of my Calabi make that here is BV operator, right? So if I would homotopically resolve this BV operator here, and so then look at what I get and what I get on the cohomology, it would be exactly the structure that so I would get studying Gromov-Witten theory of mirror-dual Calabi-Yau. But as I said, so it's just example for me, which is I just want to show you that all the structures are not empty and are related to many things around. But I have some particular goal, so to get back to the historic varieties of Ladei S.Shadrin, Ladei's realizations of S.Shadrin. So I want to go ahead and not focus on this example. Good. Interesting thing. So this is an interesting remark. So you see, so when people talk about the structures, this kind of structures, so hypercommutative algebras or CoHFTs or whatsoever, there is a very powerful tool so found by Giventhal. So this is the so-called Giventhal group action that acts on this, well, some big group that acts on the structures. And you see, I can describe very nicely what is this group in these terms, in terms of this homotopy resolution. So let me say like that. I start with the structure that I have here, so this hypercommutative algebra. I lift it to BV algebra. So let me get back to this BV algebra with homotopically resolved BV operator, and I choose a different homotopy trivialization, because I mean I can naturally twist homotopy trivialization with anything that would commute with my differential, where I get some very big group action on this type of structures, and this is the so-called Giventhal group action. But again, as I said, for me, for today's talk is just a side remark. Good. So now I want to show you some topological statement, right? Because I promised that I would have some framed little disks, well, or both. So I want to show you some topological statement, and analogous to what I just said. And so this is the statement is due to Drummond-Cole. So namely, so consider the so-called framed little disks. Namely, I consider the configuration spaces of small disks with one label on each, the boundary of each small disk, embedded in a big disk, where, okay, so here probably I will always want to have my label on the top, right? So just configuration spaces of these disks, and disks are labeled. So remember my definition of operatic. I just said that I must have some spaces of operation. So this one is going to be it's not the label that is third, but it's just the disk that is just third, right? So I said that, so the only thing I need is, first of all, I mean, I want to be able to apply the symmetric group action, which is in this case, I can just relabel these small disks inside, right? And another thing that I needed to say that I'm talking about an operatic is to have a partial composition. In this case, I can do the following. You see, I have this configuration of disks, and I want to apply a partial composition, so it's circ3, with another configuration of disks. What would I do? So I would just say that, let me take this disk, this big disk, so rotate as a whole in such a way that this label here would match that label there. So then I want to rescale it to match the size of this disk and put it there inside, right? And so then, I mean, the boundary of this third disk that I had originally, it just disappears, right? So I get a configuration now of 5 disks in this example, right? So what I do, I take this configuration, so rescale it to match the size of this disk, rotate to match the labels, and put inside, right? So this is a nice operatic. And if you think a little bit about this operatic, so I can still compute the homology of this guy. And so what I would get on the homology would be exactly the structure of BV, not the structure, but I mean the spaces of operations in BV operatic. So somehow it's a kind of, I mean, equivalent way to say things, right? So I can talk about action of BV operats, or I can talk about representation of this topological operatic, but then I have to pass to homology to get BV structure, right? And the point is the following. So I don't want to discuss in which sense I want to take a homotopy quotient, but so I want to take a homotopy quotient modulo this action of S1. Remember, I mean, I have an actual action of S1 here, right? I can just rotate these labels, right? I can rotate these labels, and this would give me an action of S1. So the point is that if I would take in a proper way a homotopy quotient model of the natural S1 action, on these spaces, what I would obtain would be the moduli spaces of curves of genus 0 with Mach points, right? So somehow it looks similar, but I have something else, namely I have this actually boundaries, right? But so actually there is this relation. So this is a theorem, as I already mentioned, by Drummond-Cole. Yeah, so maybe well, I heard that it was conjectured by Kontsevich maybe 20 years ago. So it was a statement that was around somehow, was known as a conjecture, right? And then there is some statement in different direction. Namely, I can also consider the moduli space of curves of genus 0 with Mach points, right? And I can try to apply to the spaces a real orientable blow up along the boundary. And so this is the procedure. I mean, it goes from the papers of Zwiebach and also so Kimura, Stashev, Voronov. So if I would do this, so what I would get exactly these framed little disks that I just discussed, right? So there are two ways, right? So homotopy quotient moves me from framed little disks to moduli space of curves of genus 0 with Mach points, and real orientable blow up gets me back from moduli space of curves of genus 0 with Mach points to homotopy quotients, right? And so now, so let's stay here a little bit, because I mean, of course, if you never heard about moduli space of curves, then probably I told in this slide not enough, right? But the point is that, so we see that we can realize some complicated space that maybe you don't know much about, but maybe you do, but in any case, it's some complicated space. We have realized it just looking at this, at something quite topological, at these framed little disks, right? And so the question is whether we can develop any kind of theory, and so the answer is yes, we can, but I have to explain how, to realize in a similar way the historic varieties of Ladei S-Shadrin that I have started with, right? So my goal is actually to repeat this slide in such a way that instead of this thing that I have here in red, I would have toric varieties of Ladei S-Shadrin. And surprising thing, so is that to achieve that, I have to repeat just literally what I just said about all these structures, like Gerstenhaber, BV, commutative algebras, Lie algebras, what else I have said? I have homotopy resolution, framed little disks. I have just to repeat all these, but trying to construct non-commutative versions of the same algebraic structures. And if I would do non-commutative versions of the same algebraic structures, surprisingly, instead of this moduli space of curves of genus 0 with Mach points, I would arrive at toric varieties of Ladei S-Shadrin. So let's try to develop this program. So non-commutative analogs. So what is the non-commutative analog of commutative algebra? Well, so that's maybe a time to talk to the audience, but almost everybody has switched off his or her video. So, but of course, I mean, we just have to forget about commutativity, right? And then I would get the associative operator. But now look, I mean, before I was writing it as with 2 S, and now I'm writing as with 1 S, right? So why? So the answer is because I don't want to consider Sn at all, the symmetric group action. Don't want at all, right? So it means that here, the only operation that I have, if I have n inputs, I can only multiply them from left to right, and I can't reshuffle them, right? So that's the natural analog for me of a commutative associative algebra, right? So then the question is, what is the natural analog of, what is natural NC version of shifted Lie algebra? Well, that's, I have an explanation why, but so this explanation is a bit indirect. It's still the same associative algebra, but now shifted. So also just associative algebra, but now shifted. Why? Why it is the case? Well, in some sense, you see there is some duality called causal duality between algebraic structures. And if I am in the commutative world, then I can just start with the commutative algebra and construct shifted Lie algebra as its causal dual. And the point is that if I would apply the same causal duality in non-symmetric, non-commutative world to associative algebra, I would just get shifted associative algebra. So that's why I think that it is the right analog for the shifted Lie algebra. No, okay, so you can say, well, let's see, maybe it's a good one, maybe it's not a good one. Let's see what we get, and let's try to use, because remember that we had a combination of shifted Lie algebra and shifted commutative algebra that gave us Gerstenhaber algebra. What would be the natural NC analog of Gerstenhaber algebra? Okay, so I have associative operation. I have shifted associative operation that replaces me the Lie bracket. And now remember, when I apply Lie bracket to a product, I should be able to move it through the product, right? But now the thing that I can't do, I can't commute. So if I apply Lie bracket after a product from the right, I can only move it to the right, right? And if I apply my Lie bracket, well, shifted associative algebra in this case, to usual associative product from the left, I can only move it to the left, right? So that's the natural thing to do. The question is only, so whether this structure appears anywhere, right? Because if it appears anywhere, then okay, so I did what I thought was logical, and I get some structure that is relevant in different examples, right? And indeed, I mean, if you try to think, so I have, I posed here a question, whether it's a good definition, and I have several answers, and all answers are yes. So the answer yes, one, is the following. So it's indeed, I mean, the natural generalization of, so Gerstenhaber algebra structure occurs in deformation theory in some natural way. And so there is this non-commutative on deformation theory constructed by Ginsburg and Shadrin, and what replaces the Gerstenhaber algebra has appeared to be exactly the structure that I'm discussing here. So in this sense, it's yes one, but let's not limit our answers to this one, because I also have yes two. What is yes two? You see? So we started to look at the literature, and we found that for very independent reasons. I mean, so I don't want to discuss these reasons now, but they're really independent from everything that was discussed. So Kai Borisson, so that's introduced a definition of what should be a non-commutative BV algebra structure. And I want to cite the definition of Borisson. So he said that he starts with an associative algebra. He introduced a kind of what was going to be analog of BV operator, some operator of arity 1, such that this operator squared is equal to 0, and he replaced the condition that this delta is of the second order, well, or what is the proper analog of being of second order in the non-commutative world. So is this condition, right? So if I apply this operator and then triple product, so it's just the same as if, oh, sorry, I have, so this sign should be minus. It's just that this combination should be equal to 0. So instead of 7 terms, in non-commutative case, I have 4 terms, right? And so Borisson has written a paper that argues, and actually that's a quite convincing way to think why it is the right analog of being of the second order in the non-commutative world. So now my answer yes too. Let's try to do exactly the same as what we did before to connect BV and Gerstenhaber. Let's try to construct a Gerstenhaber bracket using this definition of Borisson, right? So I take associative algebra structure and I define bracket, just commuting my operator delta, just commuting, sorry, this one should be a circle, commuting my operator delta with my associative product. So the answer is, so what I get here, the properties of these two guys, the properties of this and this guy, are exactly the properties that were natural for me for completely different reasons when I was trying to define nc-Gerstenhaber. So that's, you see, I mean, kind of I get confirmations from completely different angle, right? So that these are the proper analogs of the proper non-commutative analogs of all the standard commutative structures that I had before. Okay, very good. So so let's try now to apply the same procedures what I just did. I take this NC-BV algebra and I try to homotopically resolve delta exactly the way I did before, right? Because it's just about arity 1 operations. The fact that I'm working with non-commutative, non-symmetric operations doesn't change anything with this homotopy resolution. So what we would get as a homotopy quotient. So what we would get is some structure, namely I would have operations of arity 2, independent operations of arity 2, arity 3, arity 4, and so on, totally non-symmetric, and subject to the so-called non-commutative WDV relations. So non-commutative WDV relations, so I have written them here, so very briefly, but it's the right non-commutative analog for also quite different reasons of what we have in this hypercommutative algebra, what we have in Gromov field theory, and so on. So these relations, they also occur in a different way. So, well, surprisingly, we get just another confirmation that these non-commutative structures that we studied, they were the right structures, right? And by the way, so this is also because I want to show you where does it lead us. And so if you were at my talk 3 weeks ago, then you already recognize that because I discussed exactly these structures then. But now you see they occurred completely independently and for a different reason somehow, right? But these relations, they somehow this algebraic structure that I get trying to homotopically resolve data in non-commutative BV algebra properly represents cohomology and stratification of the varieties that I had in the beginning, the historic varieties of Ladea S.Shadrin, right? So we see that we are approaching the right thing. Very good. So let me continue. And now I want to discuss the topological model. So this is a fun because topological model of nc-BV is going to be very simple. It's not this very simple but still beautiful, right? So we had this beautiful picture of framed little disks that I mentioned, right? But now I want to discuss even more simple thing, right? So let me first start with a proper description of nc-Gerstenhaber. So nc-Gerstenhaber, so I want to discuss not framed disks. By the way, so maybe I should mention. So let me go a bit back, because I didn't mention the Gerstenhaber version of these framed little disks. So I go back to framed little disks that I had there. And so imagine that I could do roughly the same, but without having any labels on these small disks inside, right? I could do roughly the same without these labels. Then, of course, I mean, I wouldn't have to rotate when I apply my operatic composition. I can only rescale the guy that I have here and insert it there inside, right? So I would get a bit less, and the point is that what I would then get, it's sort of would be a non-framed version of little disks, but what I would get on the homology in this case would be the Gerstenhaber, the opera that controls Gerstenhaber algebra structures, right? So just a side remark, because this would explain to you why I construct non-commutative rate little disks starting from a non-commutative Gerstenhaber, right? Good. So the point is the following. I want to consider a very, very simple topological operator. Namely, my space of operations of arity n would be just the product of circles where I would have n minus 1 circles. So somehow I have to think about this guy, that this is my operation. So 3 circles, and I choose a point on each of them, and my inputs are kind of between them, right? So for instance, this is the guy with 4 inputs, right? So this is the picture corresponds to a guy with 4 inputs, and this is the picture that corresponds to the guy with 2 inputs, right? So it means that if I would apply, if I want to insert at the second input this guy, I just have to put this circle at this place, right? Because this is my second input. So my inputs have numbers 1, 2, 3, 4, right? So I just take this circle and I insert it together with this label, which is here. So I just insert it here as the second circle. And yeah, so that's my operation. So now I get an operation with 5 inputs, right? So that's very easy. Looks very degenerate. You agree? But if I would think about this structure and I would think what does it induce on the homology, I would get my nc-Gerst. So it's somehow a nice structure. No, very good. So let me now, because remember, so I didn't explain this well, to be honest, but so the difference of topological realizations of Gerstenhaber and BV was these extra labels on the circles. So now I have no circles where to put labels because I just have these inputs, and these inputs are actually these spaces between circles. Agree? So how to add here some extra circle action? So I'm going to explain that. Namely, I'll just artificially add some circles at the inputs. So I have this, so these 3, so you see, I'm thinking about operation of arity 4 in this case, right? Operation of arity 4. And so before I just had, so sort of bulk part is this 3 circles that tell me what is my, roughly speaking, configuration of disks. And now at each input, I add an artificial circle, which is a sort of framing on the corresponding disk, right? So I take, well, algebraically speaking, I take a semi-direct product of this topological operator with S1. So now my space of operations, they look like that, right? So for each input, I have a particular circle. So it's 1, 2, 3. I have 3 inputs, and for each input, I have a circle. And then I have this bulk part that somehow corresponds to the configuration of disks, right? And these circles, they correspond to the labels of disks, right? And how my composition works in this operator. So you see, I want, for instance, to put this guy at the second place, right? So I write here circ2 means I want to insert this new configuration at the second input. What should I do? I should look at the angle I have to rotate here to move the standard label. So standard label for me is always at the top to the label that I actually have here. So I have to rotate with this angle all the labels at this configuration. And then I insert this configuration here instead of this red input, right? So I replace this red input by this configuration. So that's exactly what I did. And now I have to put labels. I intentionally haven't put labels in advance because look, I have to rotate this label here. This label here tells me that here I have to rotate all the labels by pi, right? So for instance, instead of this guy, I have to put a label here. Instead of this guy, I have to put a label here. And instead of this guy, I have to put a label here, right? So that's how it works. Still, it looks quite degenerate. Still, it was, well, it's a quite simple structure, to be honest. Quite simple, purely combinatorial somehow, right? I mean, of course, I have this S1 actions and so on, but still looks well, quite manageable, let us say. So, yeah, so maybe, I don't remember, by the way, what is on the next slide, because I wanted to make a statement that if you look at the homology of this guy, you would get exactly this in CBV, but I don't remember. I don't know, I haven't made that. So let me put here this theorem. So if I think about this naively defined but topological operator, then on homology, what I get is the operator of NCBV. NCBV in the sense of Borison, right? So I get NCBV on the homology of this operator. And now to statements. So that's exactly where I was leading my talk. One statement is a conjecture. But this conjecture is in many ways confirmed. Namely, so if I would take so this simple operator, and you see, so again, I mean, I have here a natural S1 action. For instance, I can, first of all, I have S1 actions somehow at the output when I rotate all the labels simultaneously, and I have S1 actions on each red circle at each input, right? So conjecture is that if I would take this new operator and take a homotopy quotient model S1, so homotopy quotient as a topological operator, so then what I would get is the toric varieties of Ladé-Assayhedra. So the guys that I started with in the beginning of this talk. Yeah, well, so I denoted by L, and to be honest, I mean, when I'm saying like this, so as I said, so I want to take this quotient as topological operator, and remember in the beginning I said that my system of toric varieties of Ladé-Assayhedra has this recursive structure that when I look at the stratification, each stratum is actually a product of smaller toric varieties of Ladé-Assayhedra, small dimension, right? So this somehow defines me also the structure of operator. And so when I'm saying that it's equivalent, I mean homotopy equivalent is topological operator here, right? So that's a conjecture. I don't know how to prove it. So this would generalize this Kontsevich conjecture and theorem of Drummond-Cole for this NC world. But what I know how to prove, because you see, remember there was 2 statements. One I said, so you can take homotopy quotient of framed little disks, again, the moduli space of curves, right? And another one, you can take the moduli space of curves and apply a real orientable blow up. And the point is that what we were able to show is that if you apply this Kimura-Stashev-Voronov construction to this system of toric varieties of Ladé-Assayhedra, if you take real orientable blow up, and you look at what kind of operatic structure is induced by the natural stratification of Ladé-Assayhedra. So then what you get, and that's a theorem, what you get exactly this, something homotopy equivalent, to be more precise, not exactly this, but something homotopy equivalent to the simple structure that just consists of circles with labels that I just described, right? So you see, I mean, it's a kind of, there are different ways how to confirm this conjecture. For instance, on algebraic level, on the level of homology, is exactly the theorem that I just mentioned, that if you take a homotopy quotient of nc-BV, you get this nc flat F manifold, or I don't know, I mean, nc homological field theory in genus 0. So it's algebraically, this conjecture is already confirmed. So it's already a conjecture for the topological statement. But the inverse works perfectly in this case. I mean, this inverse, this Kimura-Sashov Voronov construction. So which is another independent confirmation of this conjecture. Okay, so I think I want to stop here.
Sorry, I forgot to unmute myself. Thank you, Sergey. So let's thank Sergey for his great talk. Questions?
Sergey, can you recall, you told me, it is not maybe very important, but you called about causal duality during just 20. Can you recall me what is it, causal duality?
Causal duality, well, it's the point is the following, right? So well, you can define these guys, so these operats. So yeah, I can recall. So maybe I should better go here. So causal duality. So it's quite often that you can think about your operat. So it's generated, for instance, as free operat of some binary operations, right, with some properties, maybe a few of them, right? So modulo quadratic relations.
Yes.
So maybe I should better say that it's free as generated by some S2 modulo quadratic relations. And so the causal dual, well, would be the following. So I need notation for this S2 module. Let's say it would be quadratic relations R, and S2 module would be okay, G, for instance. Right. So then the point is the following. So I can take G star as and try to generate a free operat with this dual S2 module. And then the point is I can try to quotient it modulo the orthogonal annulator of the quadratic relations I had before, right? And the point is that what I would get here, so it's called the causal dual. And if your operat is causal, it means that this causal dual can be used. So it's quadratic. Sorry, it's called quadratic dual, but it's called causal dual if it can be used to construct a free resolution of your operat.
So you have here quadratic relations and here annulator of quadratic relations.
Yeah, but it's also I mean in G star, so operatic comparison with G star. So it's also quadratic relations for the generators, right? So I still consider the G star as binary generators, and this is the ideal that generates me something. So this is a subspace in G star operatic composition with G star. Right, so it's also a quadratic operat, right? So it's also an operat where all the relations for the operations that I have are quadratic in terms of the generators, right? And so example here is indeed, so if I would start and I would have just trivial as to module, right? Modulo the relation. So trivial means that it's equal to, so 1, 2 is equal to 1, right? And I would say that I have this condition, right? So then if I would like to check what happens here, so here, I mean, I have to, I was a bit uncareful here because I have to shift degrees a little bit and so on. But here I would just have this guy with shift degree, right? So shifting degree, I just put like that. So, but it still would be symmetric. And so what I would have here is annulator. So this guy, so you can think about it as a shifted covector corresponding to this guy, right? And so what I would have here would be the Jacobi identity, properly written, right, for this shifted world. So that's somehow why shifted Lie algebras are quadratic dual to commutative associative algebras. Then the point is that, so we say that they are not just quadratic dual, but causal dual if there is an externized property, namely that this be used to construct some free resolution of that guy, some minimal free resolution. But yeah, so for me, I mean, like I didn't use control duality in this talk. So for me, the only thing was what was important that you see. I mean, I know that in this sense, Lie algebra are dual to each other, and then if I would try to apply this associative algebra, shifted associative algebra is a good analog of shifted Lie algebra.
Okay, so
Thank you.
Well,
may I ask a question, Sergey?
yeah, go ahead.
Okay, if we consider this example with holes, so you, yeah,
so which one? I mean, that non-commutative one or the
first one, the first when they actually appear. No, before.
This one.
Yeah, this one, exactly. So, so you glue, so to speak, spheres with 4 holes, not with 3 holes. So it's not like well, sort of ordinary pan decomposition. It's different, or it's just for this example. No, I'm just trying to understand the setting.
No, I can have as many holes as you want. So here, if I'm thinking about, what is framed little disks in dimension 2, n. So I would just have configuration space when I have n disks, small disks inside a big disk.
Mm-hmm.
Right, labeled, of course, 1, 2.
Yes. But then you glue inside this disk. You glue
Yeah, inside any of them, I can put a similar object with a different number. So here, for instance, I don't know. I mean, so if I would remove this guy here, I can still like plug it there inside. But then here inside, I would lose this guy, right?
No. That's what my example. So is it specific for this 4 holes or it just...
No. It's just universal. It's how I plug one disk configuration into another disk configuration. But I can have any number of disks you want.
Okay. No. Okay.
So just think about this. Just think about this configuration as acting somewhere, right? You have n inputs, these small disks, and you have one output, which is this big disk, where these small disks are living. Right, so then you have a kind of way to encode some operations somewhere. So, for instance, people are using them to study the spaces of long knots because there is an initial action of this whole guy there.
Thank
see
you.
Volodya has question, right? Volodya, can you Volodya Fox?
Yeah.
Can you unmute yourself? And yeah.
If there is a way to see the commutative cases, particular case of non-commutative, or the limit of non-commutative. So if the two things are related somehow.
Yeah, that's yeah. I don't know. So we had very long discussions with Yuri Manin about that. So that's indeed, I mean, something that you see. So for us, it looks like we indeed is our non-commutative. You see, we have non-commutative analogs of everything, but they're not like perturbative deformations of commutative things, right? And there is no way to, well, no way to do it like that, right? So in this sense, it's not really the deformation quantization type of things, and I don't know how to relate that. Though it would be very interesting. So if it's possible to see it, then I would be very happy, but I don't see it.
But you can obtain commutative by taking, you know, SN quotient, right? In some sense, or like make SN take SN equivariant part, or it won't work.
Well, I would tell you like this. So you can do whatever you want with toric varieties of Latte S.Shadrin. There is no way to obtain from them the moduli space of curves of genus 0 with Mach points. So they're related in many sort of constructive ways. I mean, for instance, there is a way to relate. So if you think about them as wonderful models of the Concini Procesi, the hyperplane arrangements are related to each other, right? So, or okay, so there are ways to relate them indirectly, but not in the way that Volodya asked. Because so that's something that I would really love to see as actually sort of non-commutativity that emerges as a result of deformation, but no.
Okay.
I mean, for all the structures, I can't see this. So actually, no, not wrong. I mean, the only place where I can see this is when I replace commutative associative algebra by associative algebra. That's the only bit of the structure where I see this deformation origin, possible deformation origin for non-commutativity. For the rest is just, I mean, for various geometric and algebraic reasons. So we just declare that we have these non-commutative structures, and that is. But to be honest, I mean, so any progress in this direction so would be very interesting for me.
Okay. Other questions?
Well, a little question. If well, this S1 at the end of your talk, well, is well, can be replaced harmlessly with SL2R, or the circles by P1s of R, or this is a kind of, well, homotopically it will make any maybe non-difference, or it's important.
No, well, no, you see, so this thing at the end is, of course, I mean, purely topological. No, I mean, it's you can take any model of S1 that you want, right? So you can replace them by C stars, for instance. I mean, otherwise, well, I don't know. I mean, so I would be a bit careful, right? But so of course, I mean, when I'm making this statement, for instance, right, that if I take the real orientable blow-ups of S.Shadrin along the boundary, and I get exactly these guys. Of course, I don't get these guys exactly. I get these guys where these S1s are replaced by C stars, right? But whether I can further replace by something, well, I have to think about the definition then. But yeah, in general, at this moment, anything topologically equivalent would work, of course.
For example, the only thing which seems to be suspicious is that at a certain moment you need to rotate. You take one point and you rotate it.
Yes, yeah. So you see, I mean, that's the point. You see, the construction that I really want to apply is semi-direct product in the realm of operats. So if I can put here any group, like S1 type group that I want, but I mean, the thing that I want to have here should be G space. So if I put here a group G, so this one should be a G space, right? So, and this is kind of universal construction that I can do. Yeah? It's just universal construction in the realm of this type of operats. That if I have G spaces and I construct this non-symmetric operat just iterating these G spaces, then I can always take a semi-direct product with the group G. In the way I did here. So then I would no problem, because of course this G, it would act also on itself here on these red guys and on G spaces that are the blue guys.
Okay. If no more questions, let's thank Sergey again. Great talk. So, Sergey, could you send me your notes as usual?
Yeah, sure, yeah.
Okay. Thanks, everybody.
Bye.
See you next week.